Hi class, we'll be talking about the counting technique known as permutations. Let's start out with an easy definition. An arrangement of n symbols in a definite order is called a permutation of the n symbols. For example, how many ways can we arrange the unique numbers 1, 2, and 3? Answer is easy. Answer is 6 ways, and I'll write them out in numerical order. 1, 2, 3, 1, 3, 2, ... 3, 2, 1. There's 6 of them. Similarly, how many ways can I arrange the symbols 1, 2, ... n? There's n of them in this case. Well, I've got to choose the first one, then I choose the second, ... choose the nth. How many ways can I do that? And I just multiply all those ways together by the multiplication rule. So I can choose the first symbol n ways. Given whatever I've chosen for the first symbol, I can choose the second n minus 1 ways. Then I can choose the third symbol n minus 2 ways, and ... By the time I get to the last symbol, I don't have a choice. I can only choose it one way. I multiply all those numbers together, and you get n factorial, which I exclaim because there's an exclamation mark. As an easy example, a baseball manager has 9 players on the team. Find the number of possible batting orders. Well, that's just how do I arrange 9 distinct players? 9 factorial ways, and that's 362,880. Let's generalize the definition of permutations. The number of R tuples that we can make from n different symbols, each used at most once, is called the number of permutations of n things taken R at a time. That's a little bit more general than on the last slide, where we took things n at a time. Here's some notation. It's a definition, and it's also something I have to prove. But the number of permutations of n things taken R at a time is represented as P sub nr, PNR, and we will see, or you can just believe, that it's defined as n factorial over n minus r factorial. Note that 0 factorial is sort of defined to equal 1, and PNN, that equals n factorial over n minus n, or 0 factorial, which equals n factorial. So that's the result actually from the last slide. Example, how many ways can you take 2 symbols from A, B, C, and D? Hopefully this will clear up some of the confusion of the definition, which is kind of a long definition. Well, in this case, I want to take n equals 4 symbols, and I want to take 2, or r equals 2 symbols from those. So how many ways can I choose r equals 2 symbols out of n equals 4 symbols? Okay, let's list them out. The answer turns out to be P42 equals 4 factorial over 2 factorial equals 12. And here's the list in alphabetical order: AB, AC, AD, ... over to DC. Notice that AB does not equal BA in my list because I'm looking at 2 tuples, in which case AB is not the same as BA. So by looking at these 2 tuples, it's essentially saying that I care about the order of the symbols. That'll be a theme that recurs throughout. While I'm at it now, let's prove that equation star. Take one last look at it, and we're going to prove that thing. So here's the proof of star. PNR, that's the number of ways to choose R things out of n where I care about order. Okay, so how many ways can I choose the first guy times, using the multiplication rule, the number of ways to choose the second times ... choosing the rth. So that's how many ways to choose R out of n, caring about order. Okay, I can choose the first guy n ways. I can choose the second guy n minus 1 ways because I've already chosen the first. I can choose the third guy n minus 2 ways, given that I've chosen the other 2 so far. ... Choosing the rth guy, I can do that in n minus r plus 1. People forget about that plus 1 usually. Okay, that's fine. That's just a fact. That equals, well, it's the same line as before, except now I'm multiplying top and bottom by n minus r ... 2 times 1. So that's at the top, and I've got an n minus r times ... 2 times 1 on the bottom. So it's just a nasty way of multiplying the previous equation by 1. Okay, now I've got that nasty looking numerator and denominator, but think about it. The numerator is n factorial, the denominator is n minus r factorial. We are done. As an example, how many ways can I fill the first 4 positions of that batting order? Well, I've got n equals 9 players, 4 equals r positions. I want the permutation of 9 things taken 4 at a time. I care about the order, so that's 9 factorial over 9 minus 4 factorial, and that turns out, after the smoke clears, to be 3,024 ways. As another example, how many of these 3,024 ways has Joe Smith batting first? Here's method 1. Here are the first 4 positions. Smith, and then who knows, who knows, who knows. So this is equivalent to choosing 3 players from the remaining 8, because Smith is guaranteed that first spot. How can I do that? Well, the permutation of 8 things taken 3 at a time is 8 factorial over 5 factorial. That equals 336 ways. A second method is that it's clear that each of the 9 players is likely to bat first. Thus, forcing Smith to bat first gives me a total number of remaining positions in the lineup as 3,024 divided by 9, because Smith was just lucky there. And again, that equals 336. Let's look at another example. This is an interesting one. How many license plates of 6 digits can be made from the numbers 1, 2, ... up to 9, and I'm going to list different conditions. And notice that I haven't put a 0 there because it's going to mess things up. Anyway, let's assume that we have no repetitions. So in other words, the license plate 1, 2, 3, 4, 6, 5 is perfectly okay, but 1, 3, 3, 3, 5, 4 is not, because it's got a repetition. So if I allow no repetitions, that's the same thing as taking 6 of those 9 numbers and not allowing repeats and caring about order. So how many ways can I do that? It's a permutation of 9 things taken 6 at a time. 9 factorial over 9 minus 6 factorial, or 3 factorial, equals 60,480. Now, what if I allow repetitions so that anything's okay? Well, that just means I've got 9 numbers to choose from for the first digit, times 9 numbers to choose from for the second, times ... and that turns out to be 9 to the 6th power equals 531,000 plus some change. Then I might ask, how many license plates of 6 digits can be made containing repetitions? And I'm also not allowing zeros anymore. And all that is, using the complement rule, that's just answer B minus answer A. Anything minus no repetitions. So that's 531,000 minus 60,000, and that turns out to be 470,961. Okay, so these examples, I hope, have given you some a little bit of flavor of what you can do with permutations, and we'll enhance the discussion in the next lesson by talking about combinations. And these are getting to be kind of fun. So we'll see you in just a little while for the next lesson.